This video will give you an in-depth understanding of the history of batteries, how batteries work, who were the early innovators of batteries. It will give you a general understanding of how batteries work in our everyday lives. First, I want to start off with the history of the battery. In ancient times, the ancients were able to utilize and create their early forms of batteries. Such we can learn that in 1936, a Baghdad construction company that was doing work in Baghdad uncovered a prehistoric battery. This finding originated from the Parthian Empire and is estimated to be over 2,000 years old. This cell, which you can see pictured in the diagram here, the early makeup of it, was capable of producing 1.1 to 2 volts of energy. The Parthian Empire was located in ancient Iraq. In around 250 BC, they used batteries to electroplate silver. In more modern times, in more modern usage of batteries, we see in the mid-1600s, Otto von Guericke constructed an electric machine using a large sulfuric globe. And in the mid-1700s, Ewald Georg von Kleist developed a Leyden jar that stored static charge in a glass jar lined with metallic foil. Now this brings us to early background of innovators. We talk about Alessandro Volta, the early pioneer of modern batteries. Born in 1745 in Como, Italy, Volta was born to a wealthy noble family. At a very early age, Volta was persuaded by his teachers to enter the priesthood, while his family wanted him to pursue a career in law. However, Volta wanted to be a physicist, with a concentrated interest in electric. In 1769, at the age of 24, he wrote a treatise on the forces of attraction of electric fire, in which he asserted his theories on electric phenomena. Volta's early work, which was well prior to inventing the electric cell battery, had made him a well-known scientist. Volta's earliest great contribution to science and his earliest work was the voltaic pile. The voltaic pile was one of Volta's earliest trial runs and earliest works. As seen here as this diagram seen here, the voltaic pile's composition consisted of an alternating zinc and sulfur disc, separated by layers of paper and cloth soaked in a sodium hydroxide or brine solution. To create this battery, he made a stack of alternating layers of zinc, blotting paper soaked in salt water, and silver. The top and bottom layers must be different from each other. If a wire is attached to the top and bottom, the pile can be stacked as high as desired, and each layer will increase the voltage by a fixed amount. Now I want to talk about what a battery is, how a battery can be defined. A battery can be defined as a chemical device for the storage of electricity. Since electricity cannot be stored directly except in electrolyte capacitors or superconducting coils, both of which have major technical and economic limitations, it is therefore necessary to utilize an indirect form of storage. Batteries can also be defined as a self-contained chemical power pack that can produce a limited amount of electrical energy wherever it is needed. These useful handheld devices that are commonly used in everyday life can convert chemicals packed inside into electrical energy, typically released over a period of days, weeks, months, or even years. The main components of a battery are anodes, cathodes, electrolytes, anions and cations, and other small components. This will bring me to telling you how a battery works. The electrolyte that releases electrons during an energy discharge is the anode. The electrolyte that absorbs the electrons is the cathode. In a discharging battery, the anode has a negative charge. The cathode has a positive charge. Batteries collect on the negative terminal. If a wire is connected between the negative and positive terminals, the electrons will flow from the negative to the positive side quickly. This also tends to be very dangerous, especially with large batteries, so it is not something you'd rather want to do. Normally you connect a load to the battery using the wire. This is a basic understanding of how the internal reactions take place inside of a battery. For example, the simplest battery that can be created is the zinc-carbon battery, or the zinc and carbon battery. Inside it, the acid molecules break up into 3 ions, 2 hydrogen-positive ions, and 1 sulfur oxide negative ion. The zinc atoms on the surface of the zinc rod lose 2 electrons to become zinc double positive ions. These zinc ions combine with the sulfur oxide negative ion to create a compound which dissolves in the acid. The electrons from the zinc atoms combine with the hydrogen ions in the acid to create H2 molecules, or hydrogen gas form. The next important topic to discuss is how to conserve battery energy and what type of forms do batteries come in. Batteries can be primarily classified as 2 main types, primary and secondary. Primary utilizes chemicals only once in a single discharge and are then thrown away after usage. What are the advantages of a primary battery? Primary batteries are non-rechargeable. They do not wear out as easily, meaning they have a longer shelf life, longer usage life. The raw materials that go into a primary battery are aluminum, which is used as a cathode in certain lithium-ion batteries, zinc, which Galvani and Volta uncovered the electrochemical properties of zinc for batteries, and manganese, which is high-grade and high-purity manganese is in demand for lithium-ion batteries. It is used as a cathode material inside of lithium-ion, zinc-carbon, and alkaline battery forms. Primary batteries have high specific energy, long storage, and are an instant readiness, which gives the primary batteries a unique advantage over other power sources. This kind can be carried to far out locations for instant use, even after long-term storage, indicating that they have a longer shelf life. Primary batteries are readily available and environmentally friendly when disposed of. The most popular forms of primary batteries are the alkaline battery. It has a high specific energy and is very cost effective. Next, I want to talk to you about secondary batteries. This kind is rechargeable. This form is important in our daily appliances. Now, here's a brief summary of some of the secondary batteries that can be found out there that you may find when you open up an appliance and see what type of battery it uses. Some common secondary batteries are the lead-acid battery. Lead-acid, which, as the oldest rechargeable battery, is more rugged and economically feasible, but it has a low specific energy and a limited cycle count. Next is the nickel-cadmium battery. Nickel-cadmium is used where long service life, high discharge current, and extreme temperatures are required. Nickel-cadmium, or in its chemical format, NiCd, is one of the most rugged and enduring batteries. It is the only chemistry that allows ultra-fast charging with minimal stress. Due to environmental concerns, it is being replaced today with other chemistries, but it retains its status in aircraft due to its good safety record. Next is the nickel metal hydride battery. This type serves as a replacement for nickel cadmium, as it has only mild toxic metals and provides higher specific energy. Nickel metal hydride, or in its chemistry form, NiMH, is used for medical instruments, hybrid cars, and industrial applications. This kind is available in common AA and AAA batteries for consumer use that most people typically use in their everyday life. And the lithium-ion battery, which I'll cover further in this presentation. Lithium-ion is replacing many applications that were previously served by lead and nickel-based batteries. Due to safety concerns, lithium-ion requires a protective circuit. It is more expensive than most other batteries. However, a high cycle count and low maintenance reduces the cost per cycle over most chemistries. To discuss further, the more recent type that has attracted more research since the early 90s with the lithium anode. Due to the lithium battery having a high chemical activity of the lithium, non-aqueous electrolytes have to be used. A stable protective layer is automatically formed in lithium and serves as a separator. A passive film forms on the anode called the solid electrolyte interface, also abbreviated as SEI. This layer separates the anode from the cathode, but allows ions to pass through like a separator. It essentially acts as an insulator with no electrical conductivity. The last portion of this film I want to talk about batteries and discharging at high and low temperatures. How batteries behave essentially in different temperatures. Batteries, just like most other things, function best at room temperature. Operating a battery at elevated temperatures improves performance, but prolonged exposure to high temperatures will shorten the battery life. So in the long run, it's not a good idea to operate a battery at high temperature. All batteries achieve maximum service life if used at around 68 degrees Fahrenheit or slightly lower. Again, high room temperature, comfortable temperature is the best way to use batteries. Certain batteries may function at cold temperatures, such as higher caliber batteries, which can be seen in further research, further understanding batteries that we normally don't use in our everyday appliances. But in conclusion, most batteries require a room temperature to function properly. In conclusion, batteries are useful objects that we encounter in our everyday lives. They fuel appliances, they fuel other objects that we use. Batteries are very important. And with its importance, it's very important to understand how they operate, how they function, and how we can use them and use them more efficiently. From ancient batteries to Volta, to understanding our modern batteries, and batteries that may even come in the future. Batteries are an important object and should be an interesting topic of study. Thank you for listening to today's presentation.